What is quantum teleportation? Is it like the TARDIS in Doctor Who or apparition in Harry Potter? Sadly, we can't send actual physical matter by teleportation yet. Instead, we can send bits of information with the help of qubits and quantum entanglement. Here's how we do it. To understand quantum teleportation, we first need to understand a phenomenon called quantum entanglement. Quantum entanglement occurs when two particles interact in a way that even if they are separated, the two states depend on each other. We will give you a simplified example. Suppose that there are two particles which can have two color states, red or blue. They are in a superposition state. Then, we will make these two particles interact together and put each one in a separate box. Let's leave one on E11 in KAIST and send the other one far, far away into outer space. According to the Heisenberg uncertainty principle, we don't know which one is at which state if we don't open the boxes. Then, we open one of the boxes. By observing the particle, this decides which color that we see. Assume that the one on E11 was red. Then, we know instantaneously that the other particle in outer space is blue because of their entanglement relationship. This is quantum entanglement. Instead of color, all fundamental particles have a property called spin. We divide this into upspin and downspin. Because the total angular momentum of the universe is always conserved, when one particle has upspin, the other particle must have downspin. But according to quantum mechanics, the spin isn't defined. Instead, the spins are superpositions so that we know that the spins are opposite of each other, but don't know which spin is which. To conclude, both particles have undefined spins, and as we measure one, we can realize the spin of the other particle, although they are very, very far from each other. This appears to oppose Einstein's theory of relativity, which claims that there is no form of transportation faster than light. Einstein dismissed quantum entanglement as spooky action at a distance. However, many experiments from then have proved that quantum entanglement is actually real. There are many applications which use this quantum entanglement, such as quantum teleportation, quantum cryptography, quantum computing, and so on. In this video, we want to talk more about the quantum teleportation, which is one of the best known applications of entanglement. To elaborate, quantum teleportation is a process in which one particle state is transferred to another particle that is spatially separated. Simply speaking, it makes information show up from one place to another. It is achieved by sending the information of qubits. For example, we send two entangled particles, usually photons, to two different points, A and B. Then, the particle at A interacts with the third particle, particle C, of which we want to send the information of. By quantum teleportation, B receives the information of particle C without any classical communication. Let's give you a story to help understand the mechanics behind all this. Alice is an ultra-secret spy that has collected valuable information. She wants to send this information to Bob, who is in the CIA, but must avoid detection at all costs. She will now demonstrate how she sends this valuable information to Bob by quantum teleportation and its benefits. So, Alice has a qubit or quantum state that she wants to send to Bob. This qubit has the following notation. You don't need to know what every letter means, but remember the general form of this qubit that we will call qubit C. Next, Alice and Bob need quantum entanglement. A pair of maximally entangled particles are prepared, and one is sent to Alice and the other one is sent to Bob. We will call them A and B. The particles are in one of the four Bell states. We will assume that A and B are in state pi plus. Alice then takes off her sunglasses to measure or simply observe the state of her two qubits. In the quantum world, a single measurement means that light intercepts the system and creates a change in the system. Due to her measurement, Alice's two particles, A and C, are now entangled. A and B's entanglement is broken and collapsed into one of these four possible states. Note that this is a very similar form to C's initial state. Now, Bob has a qubit that contains information but can't interpret this information without input from Alice. Alice needs to send Bob 2 bits of information on A and C's current state. This is done classically. Then, Bob can apply the appropriate single qubit unitary gate to translate the information. To simplify, Bob can use a matrix to interpret the information, but needs to hear from Alex what matrix to use. If Alice sends pi plus, he does nothing. If she sends pi minus, Bob applies the matrix sigma 3. If she sends psi plus, he applies sigma 1. And if she sends psi minus, he applies a combination of sigma 1 and 3. Finally, the state of B is the same as the initial state of C. Thus, we can say that the state of C was transported from Alice to Bob. The greatest benefit of quantum teleportation is its discretion. When we use radio waves to communicate, someone can interfere with the waves and extract the information. However, quantum teleportation doesn't use an actual channel to communicate, so there is no way to find out. Also, if someone tries to access to the qubit after Bob has received the information, he or she has to observe the system, which in turn changes the system. So, the intruder has no way of knowing the initial state of the qubit. However, there are some limitations. Quantum teleportation depends on classical communication to convey the information of A state. Therefore, although the teleportation of information itself is instantaneous, it can't actually be faster than light. Also, we can't transport actual matter, only bits of information. An interesting fact is that recently, scientists have successfully transported qubits. Qubits are particles that have 0, 1, and 2 as a way of expressing information opposed to qubits that express information as 0 and 1. This can open up new possibilities as it enables us to transport more information using the same number of particles. So, we have learned about an exciting phenomenon called quantum teleportation. To summarize, it uses two entangled particles' relationship to replicate the information of one qubit to a different qubit at a different place. This phenomenon itself is faster than light, but to interpret the information, we need to rely on classical transmission of information, which is slower than light. So no, we can't actually say that this is faster than light, but it certainly is exciting. So, did you guys enjoy our video? Please leave us a comment down below if you have anything you want to say or have suggestions for our next video. Don't forget to subscribe to our channel cause we'll be back with more exciting info soon. Thank you guys, and bye bye!